Hello, chemist. It's Jolly again. Time for some more kinetics. All right, this little video is going to also be talking about the rate law, only I'm going to show you the calculations so that you can determine what the exponents and the rate constant is from experimental data. So jump to the notes real quick. So I am going to do a single reactant followed by a multiple reactant, and then I put some numbers over in my whiteboard. So the experimental data that I got from the lab is the concentration of NO2, and here are the rates. Well, what I will need to know is the rate law, okay? So I know that the rate is equal to K times the NO2. I don't even need to know what the products are because I know there's only one reactant. So there's my generic rate law. I'm going to use some algebra to actually figure out what my concentration is, or not, sorry, not what my concentration, but what my exponent is and what my constant is. And I'm just going to do that by dividing out. So I'm going to take any two of these pieces, and it does not matter which two, and I'm going to do the rate law 1 versus rate law 2, and I'm going to divide them out so that I can get away from two unknowns and go back to just one unknown. Now I like to work with, big numbers, so I'm going to put the big one at the bottom. All right, so 5.2 times 10 to the minus 6 molarities per minute is equal to K times 0.20 molarity to the X. Okay, so we'll call that 1, 2, 3, and 4. That's the second set of data. I am going to divide that by something smaller, and that is the one above it. And so 1.3 times 10 to the minus 6 molarity per minute is equal to K times 0.10 molarity to the X. Now the reason I did this is look, I originally had two variables and now I'm down to one variable, and I will solve this problem. And I wish I could do that number in my head, but my molarity per minutes cancel out, and we can rewrite it like this. The molarities also cancel out, and remember, you can take the exponent out and put it on the outside, so that's really 0.2 divided by 0.1. All right, if we calculate this out, 5.2 times 10 to the minus 6th and my calculator saying I'm tired. Okay, so 5.2 times 10 to the minus 6 divided by 1.3 to the negative 6 is, a big old 4. Now, experimental data really doesn't ever work out that nice. 0.2 divided by 0.1 is a 2. So 4 is equal to 2 to the x. So what do you have to do to 2 to get the 4? And that's squared. So x is equal to 2. So I just found the variable x, okay, the exponent. Well, now I'm going to take any piece of data and I'm going to plug this back in so that I can find k. And I'll just take the one that I wrote there first. So 5.2 times 10 to the minus 6 molarities per minute is equal to k times 0.20 molarities. And this importance was squared. All right, again, I'm going to do the math out. So it's 5.2 times 10 to the minus 6th molarities per minute is equal to K times 0.2 squared is 0.04 molarities squared. All right, going to divide both sides by 0.040 molarity squared. This one is gone. And if you'll notice, one of these molarities is gone. I still get to keep one. I still get to keep one. And so 5.2 to the negative 6th divided by 0.04, I get 0.12313. Okay, 1 over molarity minute, okay, that's my units left, is equal to K. So I know X and I know K, so I can put the real or the specific rate law. So I know that the rate is equal to 0.00013, 1 over molarity minutes times NO2 raised to the second power. The beauty is now I can plug in any rate and find any concentration, or I could plug in any concentration and find that rate. That is the power of this equation. And that's how you would find it using, just one reactant. So basic, just a little bit of algebra, canceling out. It is not any different when we're going to do more than one. So stop this, go back out to the notes. What happens if you have more than one reactant? You just have to choose wisely to make sure that it will cancel out. So for instance, let's see, I like this one and this one because these will cancel out. Okay, so I can find the exponent on the B, or sorry, on the A. Now I need to be able to find it on the B, so I need A to cancel out. So any of these combined together will give me the exponent on B. So I'm just going to use those numbers. And I might try and do it right here. I'll try and write really tiny. I know that's hard for me. All right, so I'm going to take these two. I like bigger numbers, so I'm going to put this one on the bottom, 0.40 molarities per second is equal to K times K. The rate law would be A to the X, B to the Y, okay? And going to plug in numbers for those. I'm really not going to have enough room. 0.40 molarities per second is equal to K, and A is 0.20 m to the X, and 0.10 m to the Y. And I'm going to divide that by the one above it, 2.0 molarities per second is equal to K times A is 0.10 to the X, and B is 0.10 to the Y. The reason I chose that data is, guess what? The K's are gone and both of the Y's are gone, and I am now left with just solving for the X. So 0.4 divided by 0.2 and 0.2 divided by 0.1, I'm going to get, let me see, 0.4 divided by 0.2. 2 is equal to 2 to the X. So X in this case is 1. X for this one is going to be the number 1. Now I'm going to do the same thing, but cancel out A, okay? I'm going to cancel out this first section. So which two pieces? Let's just do those two pieces. All right. I'm just going to sneak down here onto the next page. All right, so 2.4 molarities per second is equal to K times 0.3 molar to the X and 0.2 molar to the Y. And I'm going to divide that by one that is smaller than it. So 0.6 molarity per second is equal to K. The A is still 0.30, but the Y has now changed to 0.1. All right, guess what? My K's are gone, and so are my A's. Okay, so that variable X is gone. And so 2.4 divided by 0.6, 2.4 divided by 0.6 is 4, is equal to 0.2 divided by 0.1, 2 to the X. So in this case, that's a Y, not an X. Y is equal to 2. So I now know two of the pieces. I know X and I know Y, and I am just going to solve for the K value. And because I can, I'm just going to do a little erase right here so I have room. And it does not matter which piece I use. I can use any of those data points. Go back to black. All right, so I know that 0.20 molarities per second is equal to K, which is I'm trying to find. 0.10 molarity, and X was what? X was 1, and 0.10 molarity, and Y was 2. All right, so I'm going to get 0.20 molarities per second is equal to K times 0.10 m times 0.01, I believe, molarity squared. I'm going to divide both sides by this value, and it's 3. I really don't have enough room, do I? All right, so 0.20 molarities per second is equal to K times 0.001 molarity cubed. Divide both sides by 0.001 molarity cubed. I am going to lose two of these, or sorry, I'm going to lose one of them and keep two of them on the bottom. So one molarity will cancel out. So my unit is going to be 1 over molarity squared seconds. And for the value, 0.2 divided by 0.001 is equal to 200. So with sig figs, and I was in seconds. So my K value is 2.0 times 10 to the second, and its unit is 1 over m squared s. And if you want the entire rate law, the complete rate law, you just plug in those numbers. And go back to my nice little eraser here. Come on. And I'll put all those pieces together. The only reason I didn't go to the whiteboard is I knew I'd forget those numbers if they weren't right in front of me. All right, here's the complete rate law. The rate is equal to 2.0 times 10 to the second, 1 over m squared seconds, A, and it was to the first, and B was to the second. So it's first order in A, second order in B, and it's third order overall. And that is how you do multiple reactants, multiple. But I am going to go over to the whiteboard, and we are going to talk about those units on the K value. The rate constant units are very important because they will tell you what order the reaction is, the overall order of that reaction. And so I'm just going to solve for the units. So I'm not going to have numbers, but I'm just going to solve for the units so that you can see where they came from. So if I'm 0 order, rate is equal to K times the concentration raised to the 0 power. Okay, so I'm actually looking for the units. So I know rate is always molarity per time. So I'm just going to use second. Okay, K and a molarity to the 0. Well, anything raised to the 0 power is 1. So this goes away as the big number 1. And so what are the units on a 0 order? K, it should be molarity over time. All right, how about first order? Let's try that. All right, this did not change. So molarity over second is the rate times K, molarity raised to the first power. So if I divide both sides by the molarity, those go away, and the unit is inverse time. For second order, still rates are always concentration over time, but my molarity would be squared, and if I divide both sides by m squared, one of them goes away, and I'm left with 1. So I get 1 over molarity time, and I hope you're seeing a trend, okay? The next one, I can predict without even doing it. It should be 1 over m squared time. And then you could just keep going and going. Divide both sides by m cubed, and I get to keep 2 of them. So the units are very, 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 very important. And you will always know them because zero order is always concentration per time. First order is always inverse time. Second order is always 1 over concentration, 1 over time. And third order is 1 over molarity squared. And the time is on the bottom as well. So that is how I came up with the constant units. And the last thing for this little video is I gave you a wonderful little sheet right here. As we all know, Jolly should not do math in her head, but some of you can do math in your head and you like those relationships. So I got this from various textbooks, kind of put together things, and I want to explain how it works because it's a nice double check. All right, if you double the concentration, if you double it and it does absolutely nothing to the concentration, what it's trying to tell you is it must have been raised to the 0 power. Okay? So if you triple it and it does not change the rate, that means it was raised to the 0 power. If you quadruple it and it doesn't do anything, that means the 0 power. But if you double it, okay? So if you double it and the rate doubles, that's first order. If you triple it, okay, and you end up with again tripling, that's first order, and again quadrupling. So you'll be able to kind of compare and contrast those. Ah, look, if you double it and it squares it, let me see, so that would quadruple it. Okay, so if you double the concentration and it basically doubles the rate, that is second order. And third order. Again, this is just using ratios, I guess, in your head, but let's see if we can figure out how to use it on this earlier example. All right, could we have done this a lot faster? The answer is yes. Okay, but math never hurts. All right, so what factor did I change the concentration? So if you'll notice, those stayed the same. Those stayed the same. So this doubled. Okay, so I doubled the concentration between here and here. And what happened here? I also doubled. So if I doubled this side and I doubled that side, the order must have been 1. The order must have been 1. All right, let's look at the y. From here to here, I doubled. But what did I do to the rate? I quadrupled. Okay, so if I double the concentration, if it multiplies it by 4, then what do you have? This is an order of 2. Now again, I like to do that as a double check, but I always do the math because, as we know, trying to do ratios like that in my head, just not a good thing. But this is here to help you if it works. If not, the math will always be there for you. All right, that takes care of trying to figure out all of those variables in the rate law. Until next time, jolly out.